All of that. All your statements.
Okay, so we're gonna start in with this. So we're gonna start on this side, it's called mix 6. Let's start with that. Sam's not here. Okay, I think he told me that. So I hope I have enough of these. Oh, you guys are? All right, everybody get one? All right, let's go. We gotta go through this kind of quickly. Population, constant rate, then this, okay. Like the exponential population model, we have 200 bacteria. Increasing at a rate of 25% a day. So what's going to go in the parentheses?
1.25.
Yes, indeed. And there we go. That's it. Easy enough? All right, what about number 2? The population in the year 2000 was 7,000. It increases at a constant rate of 2.75% per year. What will be the population in the year 2020? So, what's that one gonna look like? 7,000 times what's my ratio here? 1.0275. So this would be my formula right here. But now I need to actually use the formula. So this 7,000 is the initial population in the year 2000. I want to know the population in the year 2020. So what am I going to do? Put in 20. I'm going to find P of 20. Yeah. And I will put that into my calculator. And it isn't going to come out to be a whole number, so I'm going to round it off to the nearest whole number. Because these are people.
Super close.
Super close, good.
Yeah.
Round it off to the nearest whole number. What is it, Violet?
12,042.99.
So 12,043. Everybody good with that? Okay. How about number 3? Population is changing at a constant rate. Initial population is 20. Match the equation with either growth or decay. What's the top one? Decay. How do you know? Because you're multiplying by a number less than 1, and that makes your answer get smaller. So what about the second one? That's growth. Third one is growth, and the fourth one is decay. Very, very, very basic. Remember graphically, this is exponential growth, and this is exponential decay, right? Okay. All right, number 4. So they give me this formula. Negative 0.1. Show that the half-life of cobalt is approximately 5.26 years. We're going to do this problem 2 ways. One is a little more difficult than the other, but it's something we're going to need to be able to do later on in the unit. So we're just going to start practicing right now. Who has a thought? Who has a thought? Yeah.
Would you take that? Wait. And divide it by 2, but then also put in 0.26
So she's suggesting that we find C of 5.26. And what should the answer be? If 5.26 is the half-life, then this answer better turn out to be 4. Well, let's check it. You could, or let's just see if we can type this in. Can we type that in? How do we get E? Do we remember? Second ln. Wow. I got that. So would you say 5.26 is a good estimate of the half-life? Yeah, it truly is. Now I do want to do this problem, so before I go any further, everybody okay with that strategy? That's a good strategy, great strategy. What if, though, they gave me this equation and they said, find the half-life?
We put 4 in on the left side and then take the natural log.
So 4 equals 8e to the negative 0.13177t. Do you understand what Patrick's saying? We don't know the half-life. We're trying to find it. So he says, okay, the half-life would get me from 8 down to 4. And in fact, when I divide both sides by 8, I'm going to get that 0.5. That's my half-life right there. Now, we could solve this graphically, but I want to do what he said because we have to know how to use logarithms in this unit. So, when I have an exponential, when my variable is the exponent, I need to get it down. I can't solve for it when it's up high. I need to get it down, and the only way to get it down is to take a logarithm, use a logarithm. So he said use natural logarithms, and why would that be the best option? Not the only option. You can use any logarithm you want, but why is natural logarithm a good idea in this problem? Because we have an e, and the base of the natural logarithms is e. These are inverses of each other, and they cancel out. So ln 0.5 equals negative 0.13177t. Now, you may be a little rusty on that, but that better look familiar to you, somewhat familiar. You've seen that before. You did a lot of it last year. And then we're going to divide. And lo and behold, when we type this into our calculator, we're going to get the 5.26 as our half-life. Yep, sure enough. So I love what Caitlin did. They told me the half-life, so she just plugged that number in. That's great. If you don't have the half-life, then you have to set something up like this and either solve it with logarithms or solve it graphically on your calculator. Wonderful, wonderful, wonderful. Number 5. I'm going to do the same thing with number 5. Solve it a couple different ways. Logistic growth is another population growth model. Suppose the population of deer in a state park is this. This is not exponential. Would everybody agree with that? This is not exponential. It has a little exponential component. But that is what we call a logistic equation. Logistic equations typically look like this. And they're used as population growth models, and actually they're better than exponentials, because if this is my population growth, let's just say that's the population of turtles in a pond, okay? And they keep reproducing and we're getting more and more and more turtles. Why would this model of the population growing, why would that one be more realistic than this one? Charlie?
Because you can only fit so many turtles in a pond.
Exactly. And with an exponential model, there's no capping it, right? It just keeps going. With a logistic model, there is an asymptote up there that it's called the limit to growth. That's actually what it's called, the limit to growth. All right, so that looks something like this. And we are going to answer the question, which was what? When will the park contain approximately 600 deer? So what does that mean in terms of the equation? Do you want that to be 600? Read the problem, guys. It says D of T models the population of deer T years after we start counting. Could I solve that on my calculator? Graphically? All right, go ahead and do that. Let's solve it graphically. You think about 18.718 years. Somebody agree or disagree with me if you would. Agree? Good. Okay, now we're going to solve that same equation. This was our equation. We just did it graphically on our calculator. Now we're going to solve it by hand using logarithms. All right, so imagine, and we're going to use our calculator, but not for graphing. We're not going to graph this. So what do you think would be the first step to solving that equation?
Multiply the bottom of the fraction by 600.
Yeah, bring it over. In other
Yeah.
words, so we're going to have 600 plus, what is that, 60,000 e to the negative 0.2t. So he said bring this over here. Right? Celeste, is that what you were going to say?
Yeah.
All right. Oh shoot, I never took his hand. Sam is missing, he's the only one, right? Oh, no, Maisley. Okay, now what would I do? How about, let's subtract that 600 over. So what is that? Now what? because that's not my answer, I'm just gonna type it in my calculator anyway. How do I go next here? What do I need to do?
Natural.
Yep, I need to ln both sides. So negative 0.2t will be the natural logarithm of this big ugly thing. And then t will be that divided by negative 0.2. Bless you. Again. Oh my gosh, what happened? Did you get exactly the same answer? Of course you did. So this is called algebraically. We're doing it with like equations and stuff. And then when we did it the first time, we did it graphically. That's called graphically.
Oh,
All right, here we go, last one. Rumor spreads logistically, so we have another equation that looks like this one. Can somebody tell me why for this problem, which is about like our school starting a rumor, why would a logistic model be better than an exponential model? We're talking about in the rumors in the school, Chloe?
there's only a certain amount of people in school.
Exactly. We're capped, right? Okay, good, perfect. All right, Sam says there were 19 students who initially knew the rumor. Is Sam basically correct? Leo, what's your thought?
Because if you put 0 in for t, then you get 10.
Exactly. You guys, the initial value is the y-intercept. Let t be 0. And if you put 0 in here, then you have e to the 0th, which is 1. So 1 plus 19 is 20, and 200 divided by 20 is 10. So the initial value is 10. Unlike an exponential, where when you write the equation of an exponential, you see the initial value right there. You do not see that in a logistic. You have to figure it out like we did. We good? All right, flip it over. We have our 4 basic exponential shapes. Can we match them? Number 1 equation goes with which picture, do you think? Caitlin? C. Number 1 equation goes with C. I don't have those memorized. I know this is 4 times 3 to the x. That's exponential growth. If I make this negative, then that's going to turn this over. Is that C?
Oh, that's B.
So I think it would be B, wouldn't it? Now you think about it however you want, but how I think about it is, I know this is exponential growth. When I put a negative in front, it's going to turn that upside down. So number 1, I think, is B. Number 2 is A, because that is your growth, 5 to the x. That leading coefficient means nothing in terms of the shape of the graph unless it's negative. It changes the points on the graph, but not the shape of it. So that, number 2 is A. What about number 3? That's D. That's decay. And then put a negative in front of that, and it becomes C. Anybody have a question about that? Good. All right, number 5, write limit statements. I can't remember, did we get to this the other day? Yeah? All right, so we don't need to spend a lot of time on it, but let's do it. On the left, it's gonna be the limit as x approaches negative infinity of our function. And on the right, the limit as x approaches positive infinity. So, think about number 5. Which picture above there does number 5 match up with? A. Kids, again, don't let the 3/5 bother you. It's positive, that's all I care about. That 4 is a little biggie, that's growth. So it's letter A. So the left side is 0 from the top, and the right side is infinity. We okay with that? All right, how about G? Which picture, since we got them all there, let's use them. Which picture does G match up with? G is growth, upside down. So isn't that B? So on the left, it's 0 from the bottom, and on the right, it's negative infinity. Number 7. Which picture does 7 match up with? Did you say D as in dog? Yeah. Yeah. 7 matches up with D as in dog because it's exponential decay. So on the left, our limit is positive infinity, and on the right, it is 0 from the top. Growth or decay, number 8, that is a growth. Number 9 is a decay, and number 10 is a growth. Now, when those questions get a little bit crazy is when you've got stuff like this. Like this. Now, I'm going to start with that because that right there is decay. Would you agree with me? But I put a negative out in front of it, which turns it over, and that's actually a growth equation. All right. The sheet. Okay, first, did we finish our notes? I can't even remember if we did that. Did we do the back of page 9? We need to do that right now. Back of page 9. Check your understanding. We're in our notes packet, or big thick notes packet, and we're on the back of page 9. All right. So let's hear your ideas about problem number 1. She's going to give you a penny for be 2 cents, and the third would be 4 cents. Would you agree with that? How much money do you get on the third job? We're on the back of page 9. Write a rule that gives how much money you will make on the nth job. Arithmetic or geometric? Geometric. So if I think of it as a sequence, could I take 0.01, that's my first job, times 2 to the n minus first? That be okay with everybody? So there's a rule. All right. And then on which job will you first make over $1 million? I really don't want to just keep going. Can I use this to help me with that? How would that work? Plug in $1 million right here. And then, could I solve that graphically? Yep, I absolutely could. Could I also solve it algebraically? Yeah, so let's practice that. What's the first step? If I choose to solve this with equations, then step 1 is going to be divide by 0.01. Lord, what is that going to be? 100 million? Then what? I can't divide by 2. 2 is the base of the exponent. So at this point, I'm going to need my logarithms. Now, can I ln? Absolutely. There's no benefit to it, but you can ln, or you can use regular log. Either one, you're at the same work. So I'm going to go ahead and just log both sides. There is a little trick that we may talk about later on, but not today. Now, these do not cancel. They only cancel when the base of the, like if that had been a 10, I could cancel. This base is 10, that number's 2, they don't cancel. So I'm gonna take my exponent and bring it out in front. I know that seems like magic, and I always think of it as magic. It's a property of logarithms. We're gonna spend more time on that when we get a little further into the chapter, but do you remember doing that? Pulling the exponent off? Then I'm gonna divide by the log of 2. And then I'll add 1. So I'll just add 1. 6. She makes $1 million at the 27.575 job, so it would have to be the 28th job. The 28th job, she'll make over $1 million. When you think about that, isn't it amazing? I remember one of my first years of teaching, what would have been early 80s, mid 80s, teaching second year algebra. A girl came into the room and she said, Mrs. Ford, my dad and I were watching TV last night, and they said something on the TV that can't possibly be true, and my dad thought maybe we could work it out in math class. And I said, okay, what is it? And she said, they said on TV that if you, have I already told you this story? That if you put one checker on the first square of a checkerboard, and then 2 checkers on the next one, and 4 on the next one, and 8, and so on. So you know what a checkerboard looks like. We're making little piles of checkers, and each pile is twice the one that was before. The claim on the TV had been, by the time you get to the last square of the checkerboard, you'll have enough checkers to reach the nearest star. Well, even if you count the sun as the nearest star, that's what, 10 to the 7th, and at 93 million miles away, it's like 10 to the 7th away. Miles? That's incredible. I said, well, let's figure it out. So would you agree that's an or a geometric sequence? So we can kind of use the same formula to figure it out. How many squares on a checkerboard? Anybody happen to know that little fact? 64, good job. So I'm gonna put 64 in. So what's 2 to the 63rd? Quite large. But remember, that would be the number of checkers. Okay? So, here's an inch. How many checkers in an, stacked on top of each other? 5? You got skinny checkers, but I'll go with it. I'll say 5. All right? So now I know how many inches of checkers I have. I divided by 5. So now I'll divide by 12. And that'll be how many feet of checkers I have. And then I'll divide by 5,280. This is how many miles of checkers we have. Isn't that incredible? That is amazing to me. By the way, you know who the girl was that came in and said that? You guys know Daniel Michael? Alice? Their mom. Very smart. She came in and asked that question. All right, sometime I'll tell you, I got another story about geometric sequences. I'm not very proud of it though, so I won't share it with you right now. Number 2, sometimes the video's not really maybe I'll share it. Identify whether the following scenarios represent exponential growth, decay, or neither. You buy a car that loses 20% of its value every year. Decay. What's your ratio? What's your base that you're multiplying by? 0.8. A restaurant job shares 3% of its total sales for each shift with its employees. That's neither, because we're not growing 3% each shift. We're just saying, okay, shift 1, we made $300 and you get $9. And shift 2, we only made $200, so you only get $6 or whatever. The battery life on your phone decreases by 10% every hour. That's decay, right? You deposit money into an account that pays 4% interest each quarter. Number 3, if the initial population of rats, was 20, and it grew to 25 after the first year, which of the following best models the population of rats with respect to the number of years if the growth of rats is exponential? Do you understand that given just that first clause, it went from 20 to 25, that you have no idea whether it's arithmetic or geometric? So they told you it is exponential. So which one of those little equations would be the best? Can we rule any out? Not A, and it's not D. So it's one or the other. We just need to really figure out what's the ratio. What? do you think? Did you say B or C? B, and why did you say B? 25/20ths reduces to 5/4. So we are multiplying by 5/4. Very, very good. Okay. A while back, I gave you another sheet, which I don't seem to be able to locate right now. Oh yeah, here it is. It was a 2-page packet that said 2.1 and 2.3 worksheet at the top. And I know we did the back of the first page already. So it looks like this, 2 pages stapled together. Says 2.1 to 2.3 worksheet at the top.
I was that last
If they heard that there. Okay. Let's go to the second page. And we've already done this, but done this kind of thing today, but let's do it anyway. So we're on the second page. So we are in this little packet that is called Worksheet 2.1 to 2.3. We're on the second page of the worksheet, which is called Worksheet A, tab at 2.3. And let's take a moment and see if you can figure out what your right and left side limits are to these first 6 problems. And then let's have you come up and put your answers on the board. So I'll do the first one so you get what you're supposed to be doing. So the limit as x approaches negative infinity of f of x. So the first one on the left is infinity and on the right is 0 from the top, right? So I just did number 1. So I need somebody to come up and do 3, 2, 3, 4, 5, 6. Okay. Make sure when you're writing your limit statements that you're using the right function. So mine was easy, mine was F, but if you're doing problem number 2, you're gonna use G. Homework will be due on Friday. Is that what I have in Canvas? I need to fix it.
Yeah, that's what.
That's what it says. Okay. Okay, we still need 4 and 5 if we have some volunteers. see if I match. Let's see. Wow, I match all those. Nice work, people. Does anybody have a question about any of them? Whoever did this number 4 here, thank you to all our volunteers. Watch your function. Number 4, that should be a K. Not a huge deal. Really don't know how big a deal that would be, but might as well use K. Anybody have a question? Yep.
On number 6, like, I had it originally as it was a decay, and then we flip it to the other side, so it would be a growth. So I had as it goes to the right, like I had to flip.
Okay, so let's look at it. So you are exactly right. When you have pi over 4, that is 3/4 basically, so that's gonna be a decay. Then when you put a negative in front of it, it's gonna turn it and make it look like that.
Oh,
So on the left side, it is approaching negative infinity. Does that make sense? And then on the right side, it's turning into 0. Anything else on that? All right, let's do the matching at the bottom, match the graphs. Number 7 is, it looks like we're just talking about increasing in concavity. So 7 is decreasing and concave down. So that would be number 4, Roman numeral 4. 8 is decreasing and concave up, Roman numeral 3. 9 is increasing and concave down, Roman numeral 2. And then 10 must be Roman numeral 1. Is that all right? On the back, can I have 4 volunteers to give us a sketch for the description they've given you? So this is kind of backwards. They've given you the M behavior, and you're gonna draw a sketch. So 11, 12, 13, and 14. Do I have any volunteers? Okay, what's 13? What's happening with, are you gonna do it? less than 1 is gonna satisfy the conditions of the problem. Okay, what do you guys think? I match all these, do you? Yep, perfect. All right, give me a possible, there's no way of getting it exactly. Give me a possible equation for number 1 here, or number 11 here. What's a possible equation for this? Keep in mind, it's the upside down of that. Patrick?
X equals negative 5 times 3 to the x.
Times 3 to the x. What do you guys think? Is that a possible equation for what we drew? Perfect. How about this one? What's a possible equation for this one?
1/2 times 1/2 to the x.
Perfect. Remember, this doesn't matter except for being positive and negative in terms of the shape. Perfect. How about this one? This one is the upside down of this one. So f of x equals negative something times 1/3 to the x. And he wrote an equation here. His initial value was 5. We just need to stick a number in there like 2/3 or something, and that would get rid of that one. Perfect. All right. Got 2 things for you. One is this bright colored thing, because I have some colored paper. No, that's okay. No, I messed up. I gave her 2. Counting thing. This was easier on the place that I copied it from because the curves were in color. So it's a little bit harder to keep track of in black and white, but I'm sure you'll be fine. And then I'm going to give you a little review sheet that I created. So did everybody get both papers? Okay. All right, so on this pink sheet you've got, well, you're smart people, you can understand what's happening, right? Why don't you take the rest of the period with your partner and see what you can figure out? Can you figure out which function goes with which curve?